In this video, we're continuing our unit on area of moments of inertia for composite areas. And in this segment, we're going to talk about the standard formulas for the common shapes: rectangle, triangle, half circle, quarter circle. And we're going to talk about the centroidal eyes and the eye about the base of them. And we're going to use the parallel axis theorem to just start with like the centroidal axis and to get the base. And kind of go through that practice just to familiarize you with both of those formulas. And then talk a little bit about B and H and expressing the formulas in terms of B and H. So these are the formulas we're talking about, and standard moments of inertia for standard shapes, like a rectangle, a triangle, a circle, a half circle, quarter circle. And I like to rewrite these. In a little bit, we'll look at the Hibbeler formulas, but the crib sheet formulas, but I like to write them in this way. And truthfully, for students, I encourage you to write out your own version of these, because just the practice of writing them out is a good way of memorizing what they are and familiarizing yourself with them. And so notice for each of these, I give you an eye bar, which is the centroidal eye, and I give you an eye base, which is about the base of one. And we do that for the triangle, we do that for the half circle, for the quarter circle. And shortly here, we're actually going to start with the eye bar and find the eye base, or start with the eye base and find the eye bar, to just illustrate for you the use of the parallel axis theorem applied to these. And once you have the eye base and the eye bar, then it makes problems simpler. And if you understand what you're doing, if a shape already touches an axis, then you don't have to use the eye bar form. You can just use an eye base form, which comes from the table. And so if you make sure you have eye base formulas, or be sure that you understand what an eye base formula is, then it simplifies your actual problems. So this is what we're going to do. Let's do some simple calculations of these guys. And so if we go to so starting with a rectangle, I have a base, I have a height. The standard formula for the centroidal axis of a rectangle is 1/12 BH cubed. The parallel axis theorem says that I about some axis is equal to I bar plus AD squared. So if we seek an I base formula, we can say I base is equal to I bar, which is 1/12 BH cubed, plus the area, which is base times height, times the distance from the centroid to the base, which is h over 2 squared. Well, if you look at these terms, you can factor out a BH cubed, and you're left with a 1/12 plus a 1/4. But the 1/4 is 3/12. 3/12 plus 1/12 is 4/12, which is 1/3. So I base for a rectangle is 1/3 BH cubed. So anytime you have a rectangle that touches an axis, you can just use the 1/3 BH cubed formula. It's easier. Let's look at a triangle. So a triangle, his I bar is 1/36 BH cubed, and we seek an I base formula. Well, I base for the parallel axis theorem is equal to I bar plus AD squared. So I bar is 1/36 base times the height squared, plus the area, which is 1/2 base times height, times the distance from the centroidal axis to the base, which is h over 3 squared. We can factor out a BH cubed, and so we're left with 1/36 plus 1/18, but the 1/18 is 2/36, and so we have 3/36, which is 1/12. So for a triangle, I base is 1/12 BH cubed. For a half circle, I'm going to do the reverse of this. So I'm going to start with the I base. So when you're integrating for these guys, and actually I do actually do that in a document in one of these videos, one of these days, I actually will talk you through doing the integrals of these common shapes. Um, and but anyway, if you do the integral, you actually, for a half circle, you end up with an I base, which is a relatively simple formula, which is pi over 8 r to the fourth. But I'm going to start with that and try to get an I bar about this centroidal axis. So remember, for a half circle, the location of this centroid is 4r over 3 pi. So that's the distance between the two axes. So if we write the formula I base is equal to I bar plus AD squared, if we rearrange the equation to solve for I bar, so I bar is equal to I base minus AD squared. And so the I base is pi over 8 r to the fourth minus the area. This is a half circle, so the area is pi r squared divided by 2. And then the distance is 4r over 3 pi quantity squared. If you do the math, you can factor out an r to the fourth. You get pi over 8 minus a 16 over 2 times 9, which is 18. And there's a pi over pi squared, which becomes 1 over pi. And so the second term becomes 16 over 18 pi, quantity times r to the fourth. So you can write the formula this way, or 8 over 9 pi, and you'll see that in the Hibbeler sheet here momentarily. But I like to just evaluate this number, and it's 0.1098 r to the fourth. And so for a quarter circle, I'm sorry, half circle, I bar is 0.1098 r to the fourth. And that's about this centroidal axis, this direction. There's actually a different I about this vertical axis, and well, it's pi over 8 r to the fourth is the I about the y prime axis. Finally, for a quarter circle, the I base, we got the I base from integration. We got that to be pi over 16 r to the fourth, but we want an I bar. So I base is equal to I bar plus AD squared, or I bar is equal to I base minus AD squared. So I base is pi over 16 r to the fourth minus the area, which is pi r squared divided by 4, times the centroidal distance squared. And the centroidal distance is 4r over 3 pi, quantity squared. And so you factor out an r to the fourth, and you get pi over 16 minus 4 squared, which is 16, divided by 4 times 9, which is 36. And then there's a pi in the denominator, and you get 16 over 36 that way. And again, if you look in Hibbeler, they kind of give that as a complex term, but I like to just compute I bar is 0.0549 or 0.05488 r to the fourth for a quarter circle. So this gives you the I bars plus the I base for all of these common shapes, and you know where they came from. And knowing this, you can start with one and get the other, start with the other, get the other one. And well, of course, this is just a simple application of the parallel axis theorem as well. So let's compare, so my sheet. So this is my sheet that I write out, and I encourage you to write out something like this. And let's compare this to Hibbeler's crib sheet. Oh, and one more thing I want to share with you before we look at Hibbeler's web sheet. So for a rectangle and also for a triangle, I write the formula, give you an I bar is 112 BH cubed, and I give you an I base is equal to one third BH cubed. But what if that rectangle is turned sideways? What do? How do you identify the B and the H? In the Hibbeler crib sheet, he actually gives you a separate formula for the rectangle in the other orientation, and he flips the B and the H. I prefer not to do that. I like to just use one formula and let you properly identify which side is the H and which side is the base. So how do you do that? So base is the dimension that's parallel to the axis of interest. And height is the dimension that's perpendicular to the axis of interest. Let me give you some examples. Like say you have a rectangle that's 2 inches by 4 inches, and it's oriented by the x prime and y prime axes. If I want to find I bar about the x prime axis of this guy, well, the dimension that's parallel to the x-axis is the base, so I base is 4, and the height relative to the x-axis is 2. And so the I about the x prime axis is 1/12 base 4 times 2 cubed. If I want to find I about the y-axis, then the dimension that's parallel to the y is 2. So that becomes the base when I'm computing IY. And then the height is 4 because it's perpendicular to the y-axis. And so for IY, I'm going to use 1/12 BH cubed, which is the same formula, but now I'm plugging in a 2 as the base and 4 is the height. So that way I can use the same formula both ways, but I have to correctly identify which is the base and which is the height. This also happens with the triangle. So you come to a triangle. I have a triangle here that's 0.4 along the vertical edge and 0.6 along the horizontal edge. It's got a centroid. It's got an x prime and a y prime. The I bar we're going to use for this guy is 1/36 BH cubed. So which is the base and which is the height? Well, it depends on the axes about which you're finding the moment of inertia. If you're looking around the x prime, then the dimension that's parallel to the x is the base, so that becomes 0.6. And then the height is perpendicular to the x, and that's 0.4. So for I bar about the x prime axis, it's 1/36, base, which is 0.6, times the height, 0.4 cubed. With respect to the y-axis now, the dimension parallel to the y is the 0.4, so he becomes the base, and the dimension perpendicular to the y is 0.6, so he becomes the height. And so the I bar around the y-axis is also 1/36 BH cubed, but now you know that the base is 0.4 and the height is 0.6 cubed. To me, that makes the formula, your formula sheet, simpler because you're not having to give 2 different formulas for 2 different orientations. But Hibbler gives you both, and so I just want to show that to you. So when you go to his crib sheet, so for a rectangle, let me zoom in a little bit more on this guy. So for a rectangle, we have a y-axis and an x-axis. We have a B and we have an H. So the I about the x prime axis, the centroidal I is 1/12 BH cubed, as expected. And the I about the base, so IX is about the base, and that's equal to 1/3 BH cubed, as expected. About the y-axis, though, he gives you a different formula. He says IY, I'm sorry, so IY prime is 1/12 HB cubed. And so now the H goes in for the base, and the B is cubed. So he gives you the same formula over again, but he switches the H and the B. And the I about the Y axis, you use I base, and it's 1/3 base, which is the H, times the height, which is B cubed. And he gets there, but you end up with 2 different formulas for I bar and 2 different formulas for I base, and then they flip the B and the H. And I just prefer to give you one formula, a centroidal I bar, 1/12 BH cubed, and an I base, which is 1/3 BH cubed. And then you just correctly identify the dimension that's the B and the dimension that's the h. So just so you understand that. So that will help you read his crib sheet or to understand mine or to make one that works for you, however you choose to do it. Also for the triangle, it's the same deal. So for the centroidal axes, we got a 1 over 36 bh cubed, but he gives you a 1 over 36 hb cubed and a 1 over 36 bh cubed, depending on the orientation. To me, all you need is just one, and you just need to know which dimension is b and which dimension is h. But he gives you both. And also for the base, so the I base here, the I base about the x-axis is 1/12 bh cubed, and the IY is actually a different formula. He gives 1/4 hb cubed because this triangle is flipped from our orientation. This triangle is farther away from the y-axis. Our triangle touched the y-axis. And so we actually got a different IY for this guy. And so just realize what you're looking at there. So I wanted to point that out to you just so you can read this crib sheet better and decide on how you're going to do your approach.